There's a new research paper that could seriously shake up the AI industry, and I'm not saying that lightly. It's actually pretty concerning because it highlights an important issue: how reliable these AI models really are. So, I came across this tweet on Twitter, and it mentioned something pretty significant. It said that in the one preview, there's a massive 30% drop in accuracy when Putnam math problems are slightly modified. What they're essentially pointing out is that if you take a popular benchmark and make even minor changes to it, the model's accuracy takes a huge hit, dropping by 30%. That's a serious issue when it comes to evaluating these AI models. This is a big deal because, as the tweet highlights, robustness is critical. Robustness directly impacts a model's reliability, which is something we absolutely need in the AI industry. Without reliability, these models become unpredictable, and that creates major challenges for large-scale applications. Think about it. Whether you're using AI in finance or business, you need it to perform consistently and accurately. If there's such a huge variance, like a 30% reduction in accuracy just because of slight changes in the test, it's hard to trust these models for real-world use. And if a model can't handle these variations, it's not something you'd want to implement across different projects. So, essentially, the paper starts here. You can see it kicks off with the abstract, which states, as large language models, LLMs, continue to improve, many of the existing benchmarks used to evaluate their reasoning abilities are becoming saturated. This phenomenon, called benchmark saturation, is actually something the AI industry expected to happen, so it's not really surprising. What's interesting is how they tackle this challenge. The researchers introduced the Putnam Exam Original Benchmark, which is made up of 236 mathematical problems taken from the William Lowell Putnam Mathematical Competition. These problems come with detailed step-by-step solutions. To ensure the benchmark remains valid and avoid issues like data contamination, they also created the Putnam Exam Validation Benchmark. This version includes 52 functional variations of the problems. What they did here was tweak things like variables and constants to create entirely new but equally challenging problems. Essentially, they figured out a way to generate unlimited novel problems that aren't already available online. What they found is pretty significant. Almost all models show a noticeable drop in accuracy when tested on these variations compared to the original problems. For example, OpenAI's GPT-4, referred to as 0.1 preview in the paper, achieved about 41.95% accuracy on the original benchmark, but saw a 30% drop when tested on the modified problems. To put it simply, on a test that might have already been out there in the wild, GPT-4 did okay. But when they switched to a test they knew for sure GPT-4 hadn't seen before, the performance dropped significantly. Now, some of you might be wondering why they used 0.1 preview instead of a newer version, like GPT 4.0. Well, for one, at the time this study was conducted, GPT-4's API access wasn't available yet. Also, the version used, 0.1 preview, was likely the best option they had access to during their research. Now, let's talk about the two changes they made. First, there's the variable change. As I've explained before, this is the simplest variation. It's when the variable names in a problem are altered, but the final answer remains unchanged. Essentially, the problem is slightly modified from its original statement, but it's still recognizable. This type of change answers the question, which models could have trained on this variation? Next, there's the constant change. This involves tweaking the numeric properties of the problem. To put it simply, they're saying, we just altered the numbers and adjusted some parts of the text. They even provided an example to show exactly what these changes look like. Here, you can see a constant change in action. It's something stable, like these letters. For instance, they replace the p's with y's. You can also see how variables change. X becomes W, Y turns into V, and P changes to L. This demonstrates the difference between constants and variables. Now, when it comes to numbers, the variable values shift as well. For example, they changed the number 21 to 4,680. Similarly, 2011 was changed to 4,680. This showcases how the values adapt within a given framework. What's interesting is that they didn't create an entirely new benchmark. The structure stayed the same. They just swapped letters and numbers. Letters acted as constants, while numbers were the variables. This is why, conceptually, the model should grasp it easily. The changes are subtle, but they follow a logical pattern. As you can see, here's the chart that's causing a lot of stir in the AI industry. Critics, particularly those questioning the reasoning capabilities of these models, are now using this as a strong argument. What we see here is that the drop in accuracy on this benchmark is statistically significant for almost all models. The chart shows the mean accuracies along with 95% confidence intervals, and it's pretty shocking. For example, the original model starts off with around 50% accuracy, but some versions drop all the way down to nearly 30% or 35%. That's a pretty huge drop, especially when you're looking for a model that's robust enough to identify and reason through problems in a consistent manner. I've talked about this in another research paper video, which I'll cover later, but for now, we can see that the low accuracy here really highlights just how difficult this benchmark is. And while this shows that models like 01 Preview are still decent, there are concerns. For models like 01 Preview, GPT-4, CLA 3.5, and others, the non-overlapping confidence intervals indicate significant differences, which point to artificially inflated performance on the original test set due to data contamination. Looking at the numbers, we see a significant drop in accuracy across the board. GPT-4 shows the steepest decline at 44%, followed by 01 Preview at 30%, GPT-4 at 180 degrees Celsius, 29%, and even the well-known CLA 3.5 at 28.5%. These drops are substantial, especially when just tweaking a few factors. So we can clearly see that this is a problem. If we want these models to be reliable and scalable, this issue has to be addressed. You can't have a model that performs well in a controlled benchmark, only for its accuracy to plummet when it's used in real-world applications, making it unfit for practical use. I want to quickly touch on 2 points. One key thing that might explain this, which is also mentioned in the paper, is overfitting. This happens when an LLM is trained so specifically to match the training set that it struggles to make predictions on new data. Essentially, the model becomes too familiar with the test data, performing well on it, but then failing when applied to real-world scenarios. This is a common issue with smaller models, where people often say they're overfitted to test-style questions, like those found in the GSM-8K. As a result, these models, which we might think are performing amazingly, are really only excelling at answering questions that mirror the test data. This overfitting is what allows them to do so well on those types of problems. Now, another important point the paper touches on is data contamination. This happens when samples from evaluation benchmarks accidentally get mixed into the pre-training data. Essentially, what they're saying is that when you train models on large datasets from the internet, sometimes due to the vast amount of data being used, test data can unintentionally slip into the model's training data. And if the model has seen that data before, it's obviously going to perform better on those tests. This is why we can sometimes see variations in model performance when we change the test data. This is a common issue with large language models, LLMs, which is why people are often skeptical about benchmarks. Personally, I always recommend that even if there's some data contamination, you should create your own benchmarks based on the tasks you deal with daily. Then, whenever a new model comes out or an update is released, just run the same prompt through the model and see how it performs, whether better or worse. Everyone has their own unique workflows and use cases, so while general benchmarks like GSM and others are useful, our own specific scenarios sometimes make a bigger difference, and data contamination could affect that. The paper also talks about some issues with GPT-4, especially when it comes to logical reasoning. For example, in Figure 9, the model makes some surprising logical jumps and comes to conclusions without proper reasoning. This kind of behavior points to a problem in GPT-4's chain of thought reasoning, where the model seems more focused on reaching an answer than providing a detailed and logical explanation. That said, I'm not too concerned about this in GPT-4's case. When we look at the models we're using today, GPT-4 isn't really designed to be a full-on reasoning model. It can handle basic instructions, but if you want real reasoning power, that's where models like the 01 series come in. Those have much greater capabilities when it comes to reasoning, and if those models start underperforming, then that's something we should definitely worry about. Now, if we were talking about a model specifically built for reasoning that was having logical issues, that would definitely be a red flag. But with GPT-4, it's not as big of a deal. The real concern should be the gap between current tests and newer unverified tests. There's still room for improvement, especially when we see flaws in the model's potential training data, like overfitting or contamination. So this is where we get to the OpenAI 1 preview, and as they mention, of all the models, OpenAI 1 preview performed the best on the Pudum Axum task, achieving an impressive 41.9% accuracy or 99 correct answers out of 236. Other models, by comparison, scored less than 20%. When we analyze the responses, we see that OpenAI 1 preview generally followed a similar logical path as the ground truth solution. However, some of the answers contained logical errors and inconsistencies. The most notable difference between OpenAI 1 preview and the ground truth solution is the lack of mathematical rigor. While the ground truth solution makes claims and then proves them step by step, OpenAI 1 preview tends to make claims without providing justification. This isn't the ideal scenario, but since we're talking about OpenAI 1 preview, it's understandable. That said, it would be interesting to see the paper tested with the full version of OpenAI 1. In summary, OpenAI 1 preview shows potential, but there are still significant flaws in its mathematical reasoning abilities. Now, another thing we have is Apple's research paper. So this paper essentially states the same thing I covered before. It talks about how when certain things are changed in a study, the hypothesis is that this decline happens because large language models, LLMs, aren't truly capable of logical reasoning. Instead, they try to mimic the reasoning steps they've seen in their training data. And when we add just one clause that seems relevant to the question, we see a massive drop, up to 65%. I might even include a clip from that video now because it's honestly crazy how impactful that paper was. Looking back, it definitely pointed us in the right direction when it comes to AI challenges. If you enjoy this video, don't forget like and subscribe this channel for more updates. See you in next part.